In this and the following two videos, we will be looking at three subjects that follow on from quality. These are normally handled by the Quality Control Department, and they are reliability, maintenance and safety.
Reliability and maintenance are both means of ensuring quality in the real world, but they happen in different phases of the life cycle. Making a system reliable is something that must be designed in during the design and development phases of the life cycle, whereas maintenance is something we have to do to the system during its operational life so that it maintains that quality. So let's start with reliability. The technical meaning of reliability is the same as the common sense definition. That is, what are the chances of the thing working when we need it? However, in technical use, we need to quantify what we mean by reliable. Reliability is defined as the probability that a system or piece of equipment performs its specified functions within specified limits under defined conditions for a prescribed length of time. In other words, it's a measure of the system's likelihood of meeting its requirements, i.e. of maintaining its quality. So how do we estimate what the reliability of a system will be? We need to start by finding out the reliability of the components that make up the system, and this can be measured in two different ways. The obvious way is simply to state the reliability as a probability of failure over the operational lifetime, which is the generally accepted definition of reliability. This is normally used when only a few things are being considered, like engines on an aeroplane. The alternative is to use the failure rate, which is normally expressed as mean time between failures, or MTBF, or as a failure rate per unit time. We normally use when a large number of systems or components are being used and failure in some systems is expected. There are two ways to state the same thing and are linked by the expression reliability equals 1 minus time divided by the mean time between failures.
So the question now is, how do we estimate reliabilities during the design stage so we can do something about improving it while we have the opportunity? That is, before we have built it and found out its reliability the hard way when it's too late to do anything about it. Well, there's three methods that can estimate reliability. I should point out that these are not mutually exclusive. A system design team will use all three to establish the overall system reliability. For the components of a system which are already available, we can get the reliability either from batch testing, which is typically used for smaller, cheaper components that are made in large numbers, or from service experience with the components that have been used in other systems. For the new components which have not yet been made and so cannot be tested, the reliability is often estimated by considering the reliability of similar sorts of components working in similar environments. But these two methods only give us the reliability of all the components of our system, not the complete system. When it comes to the complete system as a whole, which at the moment is just a gleam in our collective eyes during the design phase, how do we get an estimate of how reliable it's going to be? Well, to get that, we will need to use a reliability model, which is a way to combine the reliability estimates of the system's elements to give an overall system reliability. This is done by creating a network model of the system, and you will not be surprised to learn that this is often done on a computer. However, the basics are very simple and easy to understand. There are only two ways that components can be logically arranged. The first way is to arrange the components in series, which represents the situation when all the components in the chain must work for the system to meet its specification. If you multiply these together, you get the total reliability of the chain, as shown here. Since reliability is expressed as a probability, and so must be less than 1, the total reliability is always reduced as more components are added to the chain. The second way is a connection in parallel, and this represents the case when any one of the components is sufficient to meet the specification. In other words, it represents redundancy. The maths here is a little trickier. An overall failure requires all the components to fail, and the probability of failure is 1 minus the probability of success. If we multiply all the probabilities of component failure together, we have the probability of an overall system failure. And 1 minus the system probability of failure is the probability of success, and that is the reliability figure we are looking for. As can readily be seen, in this case, reliability is increased by more components contributing to redundancy, which of course is what you would expect. Care should be taken about how the network is constructed. The serial and parallel arrangement must reflect the impact on the reliability, and this does not necessarily reflect the physical configuration in the system. For example, an aircraft undercarriage is physically 3 mechanisms in parallel, but as all 3 of these mechanisms are needed to land, for reliability purposes they are in series and their reliabilities should be multiplied together. So once we have a complete reliability model network for the system, the analysis then successively simplifies the overall system model by grouping components into series and parallel and then combining them using the maths we have just seen. You then repeat the process continually until only one box remains, and that is the estimate of the system's reliability. A reliability figure is often specified in the requirements, and this is verified during development by analysis using reliability models. The problem is that the figures that are arrived at by this sort of analysis during the design phase is nearly always optimistic, and the real system in operation will fail more often. The reasons for this optimism include: partly it's often difficult to get everything included, such as the electrical harness, the structure and such things. There is a common neglecting of the reliability of the switching when you're including redundant components. There are situations where systems stresses some components more than the specification, and this is not identified, and it also does not generally include manufacturing and maintenance problems. When considering system quality, it must be remembered that it is the system's ability to meet requirements that's important, not the failure of any individual component within it. A system's ability to continue to meet its requirements, i.e. maintain its quality, with failed components is known as its resilience. In a completely optimized system where all the components contribute to the specified functions, then the loss of any component would mean the loss of quality. The system would have no resiliency. Now, to get resiliency, what we have are multiple components that are used to do the same job. And if one of those components fails, the others carry on doing that job, and the system keeps going. Having more than one way to perform a function is called redundancy. So resiliency is achieved by redundancy. There are 3 routes to redundancy. The first is hot redundancy. This is where a number of components all do the task at the same time, but if one is lost, the performance of the remaining units still enables the specification to be met. For example, having multiple engines on an aircraft. In fact, this aircraft example normally illustrates a variant on hot redundancy, which is to accept a degraded performance after a loss. That is, this performance is below the full specification, but still enables the system to operate until there is an opportunity to do a repair. The second approach is cold redundancy. As before, we have a number of units, any one of which can perform the function, but in this case only one is switched on and in use at any one time. If the hot unit fails, then another unit is brought into the system to replace it. Here is an example of cold redundancy. It is the stage rig of Angus Young of AC/DC. He's not using all these Marshall guitar amplifier heads together. He needs only one, as the sound is then fed through the public address system. But these are all old amplifiers and have questionable reliability, so under the stress of touring, he can be assured of at least one working when he needs it. The final approach to redundancy is to use alternative routing. It is sometimes possible to configure the system after a component failure in a way that you can maintain the function using other components which normally would be performing something else. This is really only possible in really complex systems and where there are secondary functions that can be degraded without losing the overall system quality. An example of combining hot redundancy and alternative routing is the integrated modular avionics philosophy that is adopted on many modern aircraft. This architecture has many identical processors, all tied to a common data bus and each performing different tasks. If a processor fails, the task it was doing can be reassigned to another processor. And if the losses are so bad that all the standby processors are lost, then the functions can then be prioritised and less critical tasks abandoned to ensure that the aeroplane can keep flying. Well, now we turn to a methodology that is often used to try and capture all the ways a system can fail and what would happen if they did. It comes in two forms. The first and simplest is a failure mode effect analysis, or a FMEA, which is, as the name implies, it just looks at the modes of failure and their effect and is more normal at the component or subsystem level. The second version, which adds an assessment of the criticality of the failure on the operation of the system and therefore is more often used at the system level. Its inspiringly original name is a failure mode effect and criticality analysis, or FMEA. It differs from a FMEA by this additional evaluation of the impact of the failures, how important they are, and therefore prioritise actions to prevent or correct the possible failures. It takes the form of a table which looks at every element of the system in turn, and then for each element looks at each failure that can happen. So the document starts with a description of all the ways the element can fail, the failure modes, and then it looks at what could cause this identified failure. Then it looks at what the effect of the failure would be on the system, the effect, and then it makes an assessment of how likely it is to happen. With the evaluation of the effect and the likelihood of it, we can start to prioritise the failure modes that we should be dealing with. But to do that, we then have to go on to a full FMEA, which starts with the impact of the failure on the overall system, that is, the criticality. And then finally, what do you do about it? Traditionally, it would take the form of a table. Something like this example for an electric kettle, which of course is artificial. It was made to illustrate the point for this lecture. Real FMEAs for real systems are massive documents, and these days would normally take the form of a digital database. But the real things do take this general look, although there are many variations. And if you do a quick search on the internet, this will show you many more types and variations that are more modern than this. We've seen various different definitions of reliability, and perhaps at this point we should start to see why they exist. It really is because the way that you put your reliability requirements into the specification you're writing is going to differ depending on the sort of system you're dealing with, how many of them you're going to buy, and that sort of thing.
Yeah, it's really, there isn't a different sort of reliability, but what you're actually interested in is when you switch the thing on, is it going to work?
Yeah.
And we call that availability, but
which we're going to come to a little
which
later.
we'll come to a little later. But that's interesting if you're an aircraft operator. If you're buying 1,000 chips from somebody, then what you're interested in is whether they're going to work full stop. So you're interested in the statistical reliability. And in particular, if you're designing a system, you need to know that statistics in order to design the system.
To put it into those reliability models
That's
that
right.
we've seen.
In order to establish things like availability.
So you're going to find differences depending on whether you're buying components or complete systems, the traditions of the industry,
Yes.
And these sort of things are going to
That's
change
right.
what you're looking at, but they're all fundamentally the same thing, which is
Yes.
is the thing working when you want it to be working
Yes.
at the end of the day.
So far, we've assumed that reliability is independent of time. But in real life, it isn't necessarily so. So how do we handle changes in reliability during the lifetime of something we've made? For example, we're used to the idea that a system gets old, it gets less reliable. The maths to deal with the change of reliability with time is called the Weilbull Distribution, after Valdoli Weilbull, a Swedish engineer who highlighted the value of these distributions in reliability analysis. It was his 1951 paper that sparked a lot of interest, and despite widespread uncertainties as to the validity of the mathematical model, including some doubts by Weilbull himself, the conclusions were quickly confirmed with practical examples, which showed that the mathematical model to be both accurate and useful. There are three ways in which reliability can change with time. Reliability may increase as any problem with a system's build are corrected, reflected in terms such as wear-in or infant mortality. Another possibility that reliability is due to purely random events and so does not alter with time. And the third possibility is that as things get older they get less reliable, and what in common language we call wearing out. The Weilbull distribution is a common exponential expression that deals with all three possibilities, assuming the change of probability of failure f is an exponential function.
If we take that exponential function for big F, where big F is the number of failures, and differentiate it with respect to time, we get the rate at which the population declines, small f, as shown in equation 2. Then we can get a figure for the reliability, that is the probability of failure, by dividing the rate at which the population declines by the remaining population, which is equation 2 divided by 1 minus equation 1. And that gives us a relationship between reliability R and time T, full of these constants alphas and beta. This relation is the Weilbull distribution, which leaves us with the question, what are these mysterious alphas and betas? Well, alpha is a scaling constant. Bigger alphas mean faster change in reliability with time. Beta is in some ways more important as it defines the shape of the curve. There are three cases that the Weilbull distribution can model. If beta is less than 1, reliability increases with time, and this models wearing in, that is failures due to manufacturing factors, which good design in production can help reduce. This period is also known as infant mortality, and often the testing period is designed to cover this wear-in period before delivery to the customer. It's a technique called burn-in. The second factor is when beta equals 1. This flattens the curve so it models where the reliability is constant and also normally at its lowest. These failures are due to random events that are equally likely to happen at any time in the component's life. The final case is when beta is greater than 1, and this creates a curve modelling a decrease in reliability over time, in other words wear out, which from common experience is something we know happens due to things like just wear, material degradation, environmental damage and such things. Some aspects of wear out can be controlled with servicing and maintenance, but in the end all products have a planned life after which the reliability is expected to drop and then the system should be decommissioned.
The obvious problem here is that we need to know the values for alpha and beta in the formula, and without that it's really not much use.
Yeah, that's very true. And the only way we can get these is empirically from looking historically at what either past versions of the system we're dealing with or similar systems is the only way we're going to get those. That may sound a little late, but if you're operating, for example, a fleet of aircraft, Knowing the distributions using the data from the first planes delivered helps plan maintenance and replacements for the whole fleet later on.
So we can apply the Weilbull distribution to the final system, but what about the components that make it up?
Well, that arguably is even more important role for the Weilbull distribution. With large production runs, the reliability characteristics can be more accurately determined and in many cases known before the system design has started.
And both wear in and wear out are cases of interest. A component manufacturer will want to know the wear-in characteristics so they can plan enough pre-delivery testing to reduce failures once it reaches the customer. And they need to know the wear-out characteristics so they can give a safe, guaranteed lifetime.
Yeah, and all three of the factors that the Weilbull can model can be combined to create something called the bathtub curve. This is a bathtub curve, and it is created by superimposing the Weilbull distributions for all three failure types. It's called a bathtub curve because it looks like the cross-section of a bathtub. The shape of the curve shown here is typical of a system that is primarily mechanical, whereas if you look at electrical components, they have a much flatter central region, more like this. Knowing the bathtub curve, we can then plan the system life cycle with burn-in testing covering any infant mortality problems before the system is delivered to the customer. Then we have a planned life that is located at the time when the wear-out factors are not significant and the reliability is highest. And then at the end of its life, we can either plan more extensive maintenance to keep the system in operation or decommission it and replace it with a new system.
I think we need to emphasise that the bathtub curve only applies to each individual item and not necessarily to the production line as a whole.
Yeah, absolutely. This is a very important point to understand, and it's a mistake that's often made. If I make and operate the same aircraft for a decade, then the aircraft made in the 10th year will have the same reliability as that made in the first year. That is, it will have the same Weilbull distribution.
However, in practice, systems with a long production lifetime do get more reliable as the production run progresses. But there are different processes going on, and the Weilbull distribution does not model it. So what is going on, and how can we model it? This can best be seen on products which we used only once. Such items include pyrotechnic devices on a small scale, although there may be a dozen or more similar devices included as part of a system, or on the large scale, for instance, launch vehicles. What do we mean by reliability in such devices or systems? You take one out, put it on the test stand or launch pad, press the button and it either works or it doesn't. So what we mean by reliability, or more precisely the probability of failure, is a statistical thing. If we build 100 identical copies of the item to the best of our quality assurance system can manage, then we would expect so many of them to fail, with the usual statistical variation, of course. Actually, what we're observing is that there will always be some variation in manufacture, and the conditions under which we fire the items will not always be the same. So calling the items identical is slightly misleading. But having done enough testing to get adequate statistics, we would expect the reliability to remain constant with time. Or perhaps not. Pyrotechnics are simple devices involving a bit of chemistry and some input to initiate them. Store them in a particular environment, particularly one subject to vibration and temperature variation, like the pyrotechnics inflating the airbags in your car, and they will age. Over time, the probability of a successful initiation will fall. This corresponds to the wear-out curve in the Weilbull model, although it is not due to mechanical abrasion so much as the subtleties of the chemistry in the device. It will wear out even if it sits undisturbed on a shelf in the stores, and we can assign a mean time to failure or a life when it would be advisable to change the device out. Complex systems like launch vehicles are different. Launch vehicles like Ariane will have some dozens of pyrotechnic devices in them, but a lot of other machinery. And while the components will have been tested and checked out carefully beforehand, the ensemble only gets used when it matters once. When we talk about reliability of a launch vehicle, we're talking about the probability that it will fulfill its mission successfully, on average, over a number of similar launches, with the same design of vehicle. The people who insure satellite launchers are very interested in this figure because they base its premiums that they charge on this number. So does a launch vehicle have a fixed reliability? The figure shows that it doesn't. The figure shows the early history of the Ariane family of launchers. At the beginning of the programme, there were quite a large number of failures. But quite rapidly, the incidence of failures became rarer, although we can see that as late as 2003, there were still occasional failures. What is happening is that with each failure, there's an inquiry to establish the cause of the failure, and a get well programme that is intended to ensure the same failure does not occur in subsequent launches. So can we establish a reliability for the launch vehicle system at any point in its life? We will guess that the reliability ought to improve after each failure, but technically it's not the same vehicle after that. Even worse, the reliability probably does not change until we have a failure. And because in some respects failures are random, they depend on the vehicle encountering a particular set of circumstances which reveals the flaw in the design. So how do we deal with this? One way is to plot what my student called a tally curve. Along the bottom we have the number of the launch, and on the y-axis we have the cumulative number of failures that have occurred up to and including that launch. At first the chart looks a little irregular. The first launch was a failure, but then there were 2 successful launches, followed by 2 failures in succession, and then not another until flight 15. At this point it may be difficult to see a trend. But as we get more data, the trend becomes apparent. There is still some irregularities, but we can ask my favourite little program curve experts to find a curve that best fits the data. And now we do see a pattern. It starts fairly steeply, and over time curves over, probably asymptotic to a 0 slope if you go far enough. The curve represents an average value for the number of failures that you could expect up to that point. More importantly, the slope of the curve represents the reliability, or rather the failure probability, of the vehicle at that point in its life. And we can ask Curve Expert to provide us with a plot of this slope against time or number of launches, as in the next slide. We see that the initial probability of failure was moderately high at about 12%, but by the 100th launch it dropped to 4%. And by the end of the Ariane 4 programme in 2003, the failure probability was less than 1%, all by steadily improving the product by understanding the causes of failure.
So in the real world, where manufacturers and operators pay attention to how their products are working in real life, and in particular the accidents and failures that are happening, the system design, its production procedures and operations change over time, which improves the reliability of the later models over the earlier builds.
That's right, and so you can see the effects of that in a surprising example. Here are 2 bathtub curves. What they show is human mortality, that is, a human's chances of dying as they grow older. We can see infant mortality, and this is where the term was first used. Babies and children have a higher chance of dying for many reasons. But once having passed puberty, the chance of death remains pretty constant for a human being until they reach their 50s, when there is an increasing chance of death due to the diseases and other problems of old age.
The interesting effect here is the difference between the underdeveloped world and the developed world. And we perhaps should point out that this is data from around the 1970s. The difference is that the developing world, there is a less stressed lifestyle, better diet and better healthcare, which is the equivalent of improving the way the system, the human being, is operated and maintained. What is interesting is that this does not change the shape of the bathtub curve substantially, but shifts the curve lower, so at all points in the life cycle, the probability of death is lower.
Yeah. We covered a lot of new concepts in this video, and so we should perhaps have a quick summary.
Good idea? Well, let's do that. We started with reliability, which is a measure of the likelihood that a component or system retains the quality it had when it was handed over to the customer. And we saw ways in which that can be modelled in complex systems. That showed that a system can be given resiliency, which is the ability of a system to handle a component failure without losing its quality, and this is achieved using one of the three ways to provide redundancy, that is, using multiple components to ensure that there's more than one way of performing any given function. We then introduced the methodology of a failure mode effect and criticality analysis, a FMECA, which is the common way implementation of reliability in a system is conducted, and that's done by looking at all the components and the ways they can fail and their effect on the overall system. Generally, reliability is often considered as a single probability, whereas of course common sense tells us that reliability changes with time. For a start, we know old things are less reliable than new things, and this can be modelled using Weilbull distributions. And finally, we looked at tally counting as an illustration of ways in which we can use the experience of products in operation to improve the reliability of later builds.
In this video, we've been treating reliability as something built in from the start of life. But in real life, we do things to the system during their life to maintain and even improve the reliability. And that is what we should be looking at in the next video.